Okay, so we'll start the second lecture on electronics by Christophe. Yeah.
Thank you. Good morning, class. So we will continue. We will finish what we had on the noise last time, and then, as Etienne was saying, the second part is more oriented to timing, which is ramping up quite a lot. So we were showing last time that you can optimize the noise when you play on the shaping. This is something that you do also in your exercises, and it's interesting. And you see here some basic filtering. So of course, I don't have the time to go into all the detail of filtering. You can imagine that you can try to do better than just some very basic bandpass filtering. And so people have played quite a lot with the optimization of that, and in particular in trying to cut more of the high frequency noise, which is the one which is hurting most. As you remember, the noise is scaling with the bandwidth, and so it's the high frequency which is hurting. And so this is why people very often they put several RCs so that they cut down more the high frequencies. You can see the effect on the pulse shape. So, and then you can see here the different curves are when you play again with the number of low pass filters that you put on the high frequency range. So it changes the optimum shaping time constant. But if you look at the value of the optimum that you obtain, it's not changing so much. And so this one is the most basic one that you can do, just one high pass, one low pass, the one that we call CRRC. As soon as you put a second RC to cut down a little more high frequencies, then you see that you don't gain anything anymore. So this is why you will see in the following, most of the time people, they just use CRRC2 and then don't go to the trouble of having more stages, which usually increases the power dissipation. So this is what you will find. As was said yesterday in a question, when people want to do something more elaborate, then they do some digital filtering on top of this basic analog filtering. So this is why I put here this usage formula, which is a way to get an idea of the noise that you will get for a given preamp. So usually it's expressed in electrons. So it's just the previous formula, but with sort of convenient units. Once again, as a function of here it's called the peaking time. It's something that you can measure actually on your waveform. You see your waveform here. You see that again, when you change the filtering, you change a little bit the shape of the filters. But if you really measure just the time to reach the peak, then you don't have to know exactly what's inside the filter. So it's kind of convenient thing. And you see then it depends essentially on three terms. Again, for the series noise, the preamp noise density. So this is the performance of the preamp. It scales linearly with the capacitance. I will say a few words just later. To bring down, so this E sub n is usually something that goes between 1 and maybe 2 or 3 nanovolt by square root of that. It's not changing so much. It's essentially determined by the power that you flow in the preamp. Capacitance, so it scales also linearly. It's very easy to add a lot of parasitic capacitance and to lose very quickly on the noise just because of the parasitic capacitance. So it takes a lot of pain for the electronics, at least on the power, to bring down E sub n, and then you should not waste it by the capacitance. And then you get the parallel noise. And so usually you can measure this thing. So this is an example of measurements. And you see that when you fit, you can extract the parallel noise and the series noise, and it's the way to compare either to your data book or to the simulation that you are doing. Of course, on the series noise, you don't get directly the series noise of the preamp itself. You just get the product of the series noise times the capacitance. And the way you have to really get the noise spectral density of the preamp is to change the capacitance, as is shown here, so that you can add some known capacitance and then fit the noise as a function of the additional capacitance. And from that, you can extract the preamp capacitance and then the series noise. You have to be careful when you do that. Very often people, they fit a straight line and they are surprised to see that they get a huge and unrealistic preamp capacitance. Actually, you should not fit a straight line on that. It looks a straight line if you have a large capacitance enough, but it's not. And if you really want to extract parasitic capacitance, you need to use a quadratic fit scale here. If you don't use any shaping, which happens a lot, for example, in pixel, or if you go now directly into a discriminator, this is something that we will also see just after that when you do also for the timing. Then actually it's the preamp bandwidth which is making the low pass. So you don't have high frequency noise to the infinite. And so now the bandwidth is determined by the speed of the preamp. As you can imagine, so when you change your threshold here, when you go into a discriminator, depending on the noise, then sometimes you pass your threshold or not. The noise is helping or the noise is hurting, and you get this famous what we call S curves. So if the threshold is low enough, then you get a hit 100% of the time, and then you are reaching the signal amplitude, and then it's only the noise who sometimes make it pass or not. And then when the threshold gets too high, you never trigger. And so you get this kind of response. If you make the derivative of, again, this S curve, what you get is a Gaussian, and you directly get the noise at the output of the preamp. And so this is also a way, an indirect way of measuring your noise from the S curves when you don't have access to the preamp output. I will skip the coherent and incoherent noise, and this is where we were supposed to have finished yesterday. So I was a bit too long. I will say a few words now on a little more on what is done to design charge preamps, so that you know what the electronics guys are doing all the time and why it's taking so long to make a preamp and what are they playing with. There are many ways to design a charge preamp. So I've seen that in the lab courses, so you use a commercial op-amp exactly like we have done here. It's interesting to notice that if you just realize the charge preamp like that, it will not work. And you have seen in the lab, if you remove the resistor, which is here between, again, the input and the output, the ones who have not done the exercise yet, just remove the resistor and you will see that the preamp will stop working. And this is something that is due to the fact that actually there would be an infinite gain for the zero frequency, which is the DC. And there is always a leakage current. And so this would be a pure integrator. It's something sometimes used in astrophysics. You just integrate the light that you get from the stars, and you integrate that for a very long time. And so you try to minimize of the leakage current. So if you do that, the output will go up or down, depending whether the leakage current is positive or negative, which at some point it will hit the power supply value and will stay there until, again, you discharge your feedback capacitance here. When you put the resistor, this is what you are doing. So you can do a charge preamp like that. Actually, it's not done like that in the in all of the design that you can see in the bibliography. So if you were asked to do a charge preamp, probably the best idea is to go, of course, in the literature to do your bibliography and look what people are doing, and you will find schematics. You can go to very old schematics, and so this is one of the original design by Veljko Radeka 60, 70 years ago on folded cascade architecture. Even before that, they were schematic with vacuum tubes, but so it's not so new. There is another way, which is to look what is inside the your op-amp. So you look at the schematic of your op-amp. So I took one which is here, and then you remove all the transistors which are not useful. And so you look, you have a differential pair here. This point here is connected to ground. So this non-inverting input is connected to ground. This is an op-amp is a very general purpose device. So you have to be able to use symmetrically the two inputs. What you are doing is not at all a general purpose thing. So this thing is connected to ground. You don't need a transistor to hold the ground. You can put directly the ground on the other side, and this will work the same. So you will save half of the power. You will remove half of the components. And if you make just look at the schematic, you will just go back to the original radical schematic, again with a folded cascade on this. So this is how you arrive to this kind of schematic. This is not the only one. So I don't want to go to technical, so that you could have other ideas of preamp, and you will see, especially when you go to high speed, they will turn to be a bit different. Folded cascade is a very efficient one because you take gain in the first one. I'm not supposed to talk about transistors. I'm sorry, I get pulled up, but it's the way this one you get gain on it so that the noise of the following one is more negligible. And so this is why most of the schematic, they follow the same architecture. There is a good reason for that. And then what people are using all their time, you have a lot of questions that you can ask yourself once you have the schematic. So the type of transistor you are using, PMOS, NMOS, NPN, whatever HEMT or transistor you can use to try to reduce the noise. Then you play on the current in the transistor, you change the size of transistors, you look at the noise contribution of everything, and so on and so on. So there's a long list that you can work on, and then you do some optimization on that. This, unfortunately, I have to skip. This I have to skip. This is probably a bit also too technical. So when you get now your full schematic with the biasing and so on, this is what you will find in most of the schematic of the transistor. And then now you run simulation. Should go back one step. Is that you can make simple calculations by hand from the schematic. Nowadays, students, they tend not to do that any longer. And I think it's a pity because when you do the schematic by hand, so it's pretty simple. So once again, you just have resistor, capacitors, and current sources. So you can calculate the gain of the op-amp with some very simple formula. And you see that there are only a few parameters which impact the gain and the speed. So what we call the transconductance of the input transistor, but nothing else. And then the output conductance of the second one, which already tells you if you want to optimize some parameters, you know where to look. Now I see very often my students, well, the students tend to have, there are three parameters. They tend to do a sort of parameterized analysis with varying all the sizes, currents, and everything, and try to find the optimum. It's not the best way to do. So this is what artificial intelligence would do and arrive to the best value of the components. So sometimes it's a local optimum, which is not very stable. So it's not something that you will like. And the other thing that you will not see when you do that is if you are cornered, it will not be changing the size of the component that will help you. You will need to add a second transistor, another transistor somewhere else to counteract an effect that you have seen by your calculation, by understanding how it works. Just a global optimization is not going to do the trick. It's not going to help you find new things. It will just be artificial intelligence. Okay, then you do complete simulation. I want to keep some time for the timing, but by hand, you can only do first order calculation. It's important because you know what are the important parameters. But then you have to go into details for which the simulator is very good. And you have to test all the possible variation of the fabrication parameters, which are important for the robustness of the design. You want all the devices to work efficiently. Okay, then this is what now the everyday work of the electronics designers in the different labs. Then they lay out the device, they do different checks, and then they generate what we call the mask for fabrication. And this goes into fabrication in $1 billion foundry. And so you have all heard about the semiconductor crisis and how it's difficult to manufacture semiconductors and all these kind of things. Just taking an example of that, so a chip that maybe some of you know, which is used on again, semiconductor detector. So this is TimePix, designed by CERN. This was probably presented last week in the semiconductor session. So it's an array of pixels, 20 millimeter by 20 millimeters, so lots of pixels. Don't know what version of TimePix this is, but the pixels are typically 50 by 50 micron square. And so lots of little squares like that. They are grouped by arrays of 8 things. And if you go and look into the schematic, you will see here the charge preon that we have talked about now for half an hour and last time. Then you find your discriminator. So again, what just we showed, that you pass or not the threshold and you get a hit. And the rest of it is then all the digital circuitry. So you store your hits and the way you come and read them down. And then you have the end of column logic. So you bring all the information to the back of the chip. This is what you see here. And the data, they come out only on one side so that you can tile together all your chips. This is a zoom here of this region. So once again, this is around 100 micron by 200 micron. And you see that the analog part is this little rectangle here. There would be the preamp here, the discriminator, and some local threshold adjustment. And the rest is the digital. So you see in this chip, you have around 80% of the chip is digital design. And the analog part is only this little fraction here. Still, people, especially the analog designers, they spend a lot of time optimizing, like just we saw before, the few transistors that you have here to get to the performance. The digital design is a bit different. So the digital design is not done transistor by transistor with schematic and so on. I think you have an FPGA also lab. So you see that now this is looks more like software than really hardware, but we call it firmware. So I think this one is in VHDL or in Verilog. And so you have very elaborate tools that from the RTL description is making the schematic at the transistor level and then putting all the transistors together, called the gates that you have also in your FPGAs, and they are doing the routing. So this is not the most difficult part, but then what is important also, it's extracting all the timing information so that you can check that this thing is actually working. And so there is a lot of, again, very specific tools to do this part. And of course, once again, I don't want to go into all that, just to give you a flavor of what is going inside all these chips and why so many people are spending so much time to make these things working, because they get more and more complicated. One thing that we have, especially in calorimetry and in timing, probably more acutely than in pixels, is the fact that there is a lot, again, of digital activity very close to very sensitive analog front end. So you try to get your small signal, and then you get a lot of noise around, and you want that the digital activity, which is very synchronous, so everything is happening exactly at the same time, again, is inducing a lot of noise. This is something, one important thing to see the amount of difficulty is trying to go back again to the fundamentals and try to see what is the amount, the voltage that you have on the input, again, of your preamplifiers. And so you just look once again on the, so the voltage is the charge that you want to get divided by, again, your sensor capacitance, the capacitance at the input of your amplifier. Typical pixel, again, you get femtocoulombs, but the sensor capacitance is a few tens of femtofarads. And so this is something you get typically 10 millivolts, something like that. When you go to calorimetry, for example, let's take high granular calorimeter, which is something which we know here. The MIP is the same. The thickness of the silicon is the same, and so you get the same amount of femtocoulombs. But now the pixels in the calorimeter, they are 1 square centimeter instead of being 50 micron by 50 micron. And so the sensor capacitance is now 50 picofarad instead of 50 femtofarads, which means that on the input, you are sensitive now instead of 10 millivolts to something like 10 microvolts. And so this shows you that now the digital noise is very quickly going to make hundreds of microvolts on the ground and everywhere. And so this is something that is very difficult to fight. Okay, so in calorimetry, so you had the lecture on calorimetry. So Etienne showed you the development also on the shower, so in the crystal. The evolution of calorimetry also, you had the lecture on calorimetry. So, of course, more granularity to get better pictures of the shower, in particular in the jets. And also now also the timing information, which is also coming in. The idea is that people are going to what is called imaging calorimeters. So you are able to do particle identification and really reconstruction in your calorimeters. And so the impact on electronics, you can guess once again, is now the number of channels are increased a lot due again to the increased granularity. And so this is why the question of power dissipation is much more important than it used to be in the past. In the past calorimeter, you had space, cooling was not a problem. You could put pipes, dead material, nobody would care about that. This is unfortunately no longer the case. The need for timing, so I guess this was shown. So it's nice that you did the talk just before, because now everyone is convinced that the timing is important. And in the timing, one part is coming, as Etienne was saying, is coming from the electronics. So when you want to get the information of the time of arrival, so you get your signal from your electronics, and then you put a threshold, and you want to know when you pass the threshold. And so you immediately come into two effects. The first one is, as you can see on this plot, and probably many of you know, is that the larger pulse will cross the threshold earlier than a smaller pulse. And so we call that time walks. This is something that depends on the rise time. If your signal is very slow, this effect will be very pronounced. If your signal is infinitely fast, it will not happen at all. So this is something that has been known for decades at least. There are many ways to go around this thing. The simplest one is when you know the amplitude, you know the correction that you have to make, and then you just correct. There are also constant fraction discriminators, so that you make a sort of combination of the signal and a delayed one, and you get something which is insensitive to the signal amplitude. You could think of just making the derivative and looking at the zero crossing. So this thing is never going to change. So there are many ways around. I could say that nowadays, again, the lowest power and everything is just to get an information on the amplitude and do the correction. Second effect that you encounter is the fact that, again, due to noise, you will pass your threshold when the noise is helping or hurting earlier or later. And you have all looked in an oscilloscope at the disc. I think there is a lab class also on that. So you look on your oscilloscope on your comparator output or discriminator output, and either you add noise or you put a small signal, and then you see your discriminator output, which is wobbling like that. So we call that jitter. And so this is just due to the noise, the fact that there is noise on the waveform here. And so when you cross the threshold, it will depend on the noise and, of course, on the slope once again of your signal. It's easy to move the noise in the voltage domain to the time domain, because the slope here is just the dV over dt, or the rise time of your electronics. And so then you can show that there is a term in the measurement of the time which scales as the rise time. So another way to express that, this would be rise time, this will be signal amplitude, and this would be noise. So sometimes you will see it also in this form of rise time divided by signal to noise. And so this is why you see very quickly that if you want to do good timing, if you are fast, this helps. Okay, this you would have guessed. This is relatively obvious. The faster you are, it seems that the better you are. The more signal you have, again, it helps immediately. And so when you get a lot of light, you much better timing than when you just get a few photons. So this was also shown before. And as you could also have naively expected, this is also the more noise you have, and then the worse this is. So the other terms, the time hook, then, as I said, you can correct. At some point, there will be also noise affecting the accuracy with which you correct the time hook. Right now, people, so not sure in a full system, we are not going to be hurt much more than we think with this term here. In the test setup, this is not dominant. And then, of course, there is also the TDC accuracy. So when you convert your timing information with the time to digital converter, of course, the TDC resolution is coming into the play. So now if you go into the timing optimization, so you just go back to the formula, the noise divided by the slope of the signal. And then you say, obviously, I want to have my noise as small as possible, my signal as fast as possible, and as much amplitude as I can. And then you remember very quickly that, but the noise is scaling with the bandwidth. And so if you increase the speed, you increase the noise. We just saw that just before. But fortunately, then you remember that the noise scales with the square root of the bandwidth. And so naively, you would say, my dV over dt scales with my bandwidth, the noise is proportional to the square root of my bandwidth. And so if I just, the jitter should be proportional just to the square root of the bandwidth. And so the faster the amplifier, the better the jitter. And so there have been a lot of measurements of the timing in the community now over the last 5 or 10 years. And people have very often gone to gigahertz amplifiers, 1, 2, 5, 10 gigahertz, and trying to see whether they could improve the performance on the time measurement. And with sometimes a little bit of disappointment, as I will show in a few minutes. And the second thing that now you have in the community is that the high-speed preamp. So usually when you go and buy a 2 gigahertz amplifier, it's a 50 ohm input impedance, because at high frequency, there will be, you need to terminate properly all your transmission lines and things like that. So if you want to be able to use it conveniently with a system on the table, then you go into 50 ohm systems. And then you can ask yourself, but when I have my detector, my electronics on my detector, I will not have cable or thing like that. I probably don't need to be 50 ohms. So I could play on the preamp impedance. And then there are different views that some people say, oh, I should have as low impedance as I can, so that I just get this RC very small and then it's very fast. Or sometimes you would say, I get the charge out of my sensor as fast as I can, and so R should be as small as possible. Which again is not always the case. Just a little reminder on what we will be just discussing in the following. So in analog electronics, there is a 2 pi. It's not like a clock frequency. So 1 gigahertz is not 1 nanosecond. If you want to convert sort of, so usually when we measure the rise time, it's convenient to measure between 10 and 90%. So it's easy to see on the pulse shape. Sometimes you get other values, but it's something convenient. And just to make the correspondence, so a rise time of 300 picoseconds corresponds to a 1 gigahertz frequency, just to get the, so there is 2 pi, but there is a logarithm of 9 and so on and so forth. So this is why you get this kind of values. So that just remember 1 gigahertz is not 1 nanosecond. So the rise time, if you get 1 gigahertz bandwidth, then the rise time will be 300 picoseconds. So now coming to high-speed preamps. So if you just go around, so sometimes people have different views of high speed. So very often they see with a, inductors and chokes and things like they used to be in old radio receivers and things like that. So there is no way you can go gigahertz electronics with bricolage. That's never going to fly. Remember that again, 1 millimeter of wire is 1 nanohenry, and this is already at 1 gigahertz. This is already 6 ohms, 6.28, and so you are working with things which are low impedance, and so this is already much more than you can accept. So usually, and many of you probably know that, when you go now to high speed, this looks like more plumbing with everything which needs to be tight and screws and everything than things that you bricole. Okay. I have a short also digression on now whether you can do high speed with a charge or current amplifiers. So in order to go to the high speed, so there is sometimes a belief that the charge preamp is slow and then that you need to go into the current preamplifier. I will not, again, go into calculation all the time. So these configurations are similar. You remember that at the beginning, we did the charge preamp because we put a capacitor here because we say, oh, I want the charge, so I need to integrate the current. And so a capacitor is doing that. If I don't want to integrate the current, if I want to see the current pulse shape, then I say, very easy, piece of cake. I replace my capacitor by a resistor here. And instead of getting the integral of the current, I just get my input current multiplied by the value of my resistor here. And so this is something that is used a lot. Very often you will see that also under the term of transimpedance amplifier. So this is resistive feedback. So you conserve the signal shape, so you don't need the integral. If you're on the charge, you will need to integrate later on your current. If you do this kind of thing, I think there is a little calculation somewhere. So I will not go into the calculation. You will see that maybe this is something that they do in the lab, or you should do in the lab, because I've seen that you have some charge sensitive configuration. And at some point, I don't know if you can even get the values to reducing the resistor value. And very quickly, you will go into instability. So it's interesting to see and to notice. So it's a problem you encounter when you try to reduce the value of the feedback resistor, and that you have a capacitive detector, which is the case for what we have. I skip a little the slides. This will be an exercise for you. So you redo what we did in, you all did the exercise of redoing the charge preamp, I'm sure. Yeah. Okay, so congratulations. So now you will do it also for the current sensitive preamp. And you will look at the input impedance and you will see that it looks like an inductor. It's explained in the slide, which I just skipped. And so now you remember that if you have a capacitor and then you read that with an inductor, you have an LC, so resonant circuit. And so this explains to you why you get this kind of ringing. And the way that you remove the ringing is by having some what we call damping capacitors in parallel with your feedback resistor. And so when you do that, instead of having this red curve here that you can have in your lab thing, you will come with a something which is damped. You can come with what we call critical damping in electronics. So this is the blue one. And then if you increase the C sub F, then you will slow down and you will get the green one. So this is what you get. And to make a long story short, I think this is on this one. So in the end, you have a resistor in parallel with a capacitor. And so it's difficult to make the difference between the charge current and the current preamplifier. And it will just depend on the value of RF and CF and on the frequency at which you will be operating. After that, the rise time is not going to be different. So you will have probably maybe more stability issues with the current preamp, but that's all. The charge preamp, it's important to realize that they are not slow. So you remember they make a long short current pulse into a long output voltage. The current preamps is going to keep the current pulse shape at the input. So they are not faster, they are shorter. And there is often this confusion between the signal rise time and the signal duration. And so this is why the difference that you have here. And you will see in a minute that this will come back into the play. If you really want to be much faster, then at some point you will realize that it's difficult to get something with the feedback because the feedback comes too slow. And when you buy a very high-speed amplifier, if you make a very high-speed amplifier, or if you look at how your mobile phone antenna amplifier is done, it's usually open loop configuration, so to work into the gigahertz region. So there are two main configurations. What we call current conveyor. So we just bring the current, we copy the current and we bring it out, or what is in your mobile phone, or what is in the 2 gigahertz amplifier that you buy from mini circuits, what is called RF amplifier, which is a voltage amplifier. Once again, it's a bit technical here. We use both. So this is just for your information. There will not be much difference between these two configurations. And now one thing that you need to realize is that you have to remember when now you go to very high speed that your detector current is very often not infinitely short, in particular with semiconductor detectors, sensors, and also your detector is capacitive. And it will be difficult for very high frequency. So the detector impedance is going lower and lower. And so it will be difficult to fight this capacitive effect. So just a few examples here. The classical pin diode. So the current, so this is the current as a function of time for the electrons and the holes. So you had the lectures on that. So there is often a confusion once again on this is the current. And so the current rise time is the time it takes. So you create electron and holes in your junction. And now it's so they are at rest. And then there is the high voltage and they acquire their velocity, their terminal velocity. This process is extremely short because they are very light. And so they get accelerated very quickly until the velocity saturates. And so this is making the rise time of the current. It's very short. It's certainly less than 10 picoseconds. And then this thing, they drift at a constant speed and they get collected by the electrode. And so this is why you get this current classical triangular thing. And I don't know if you can read the scale, but for a 200 micron pin diode, the transit time would be something like 2 nanoseconds. If you go now to LGAT sensor, so we'll say a little more on LGAT sensor. This is the same than the pin diode, but there is at the end a gain stage, an amplification stage at on one of the electrodes. The current pulse shape looks different, so there is the time to reach the amplification region and then get amplified. And now again, depending on the thickness of the detector, the current duration is around 1 nanosecond, sometimes less, 0.5. And now the rise time and the fall time, they are a bit different here. But in the end, you will see that what matters is the current duration. When you go to these optical detectors, so for example, silicon PM or MCPs, then discharging the microcell of a silicon PM is very short. And so the current duration, certainly less than 100 picoseconds. So usually the detector guys, they look on this thing, they say my current is rising in 10 picoseconds. And when I send my signal in my oscilloscope with my RF amplifier, I only measure 1 nanosecond or 0.5 nanosecond. And so the beautiful rise time of the detector is spoiled by the electronics. I've heard that so many times. Well, actually, it's not always entirely the fault of the electronics, and most of it very often comes from the sensor itself. And so just looking on something, so simplifying things, well, just assuming that the current is this infinitely fast pulse with a given duration that I call T sub D, so duration of the pulse. Now adding the sensor capacitance and looking at how can I optimize my preamplifier impedance. Do I need to be 50 ohm, 5 ohm, 500 ohms, 50 mega ohm, whatever I would like. So I'm playing with this RS input impedance here. And I'm looking at the capacitance here as a function of frequency. 1 picofarad, 10 picofarad, 100 picofarad would be a silicon PM. 1 gigahertz is here. And I'm comparing this to 50 ohm. And you see that in the 1 gigahertz region, it's only the smallest capacitor, so less than 1 picofarad. So maybe the pixel, they will still be dominated by my 50 ohm. Otherwise, anything, the current will only see the capacitance here. The 50 ohm is already too large, which means that it's difficult for me to get the signal out of the capacitance here. So the current will go on the capacitor, and so the current will get integrated. If I did not have the capacitor, I would see exactly this pulse shape with an infinitely fast electronics. When I put the capacitor, now I get the integral of the pulse shape of the current. You can make a little simulation here with this kind of thing. And for example, I just take here 10 femtocoulomb, duration of 1 nanosecond. You can play a lot. Again, we play on the detector capacitance, you send that into 50 ohm or 50 kilo ohm. So whether you go into a low impedance preamplifier or what we call a voltage amplifier. And what you see is what you probably would expect is that when you go into the high impedance here, your current gets integrated on the capacitance. And so the value that you get is Q over C. So here in my example, I put 10 femtocoulomb into 1 picofarad. I just get 10 millivolts here. And then it decays with the time constant here, 1 picofarad and 50 kilo ohm. If I put 50 ohm, now 50 ohm, the impedance is smaller than the impedance of 1 picofarad. Now I see my pulse shape here that you see. You should still notice so that I keep the current pulse shape, but I did not gain on the rise time. I just lost on the amplitude, and that's all. If I play a little more now, increasing the capacitance, 10 picofarad, you see that with 50 ohm, I'm sorry, I inverted the color, so nothing changes for the voltage amplifier. I just get less amplitude because Q over C is now smaller. And if I go into 50 ohm, then I start discharging my capacitor faster than I charge it. And so this is why I don't reach 1 millivolt, and then I go down. I have not gained on the rise time. My rise time is still dominated by, again, my current duration. If I go to 100 picofarad, whether I put 50 ohm on the infinite, I just get my Q over C, and the current duration is also completely dominating the rise time. So this is just to illustrate that at very high speed, it's extremely difficult to beat the sensor capacitance, which means that you will integrate your current. And so the current duration is going to be a very important parameter. So more example of pulse shape now again, once again silicon PMs, because they are a very fast detector. And now playing a little bit with the parasitic inductance that you have in the different devices like that. When I have no, here, if I go into 50 ohm, if I have no inductor, I get the red curve here. So a very fast rise time. My signal amplitude is just Q over C. And the RC here, my 50 ohm, is making my decay time. So in no way my rise time is given by the resistor which I put here on my silicon PM. So if I put a lower resistor, it's not going to be faster. If I now take into account the inductance, my rise time starts getting degraded because I have an L over R. This is what we said yesterday. The inductor is opposing to the variation of current, so to the current going into my preamp. And so this is going to slow down my pulse, and I will see a classical L over R. My decay time will be unchanged, and you see that my signal amplitude is also unchanged. If I now want to go lower impedance, to say I want to extract the charge from my sensor, so I go, let's say, to 5 ohms. If I have no inductance, I get exactly the same signal amplitude, Q over C, and you see that the only thing which has changed now is the pulse duration. So I discharge much faster my silicon PM, and I get a shorter pulse. So this is sometimes something that you like if you are doing LIDAR readout, because you want to do double pulse separation. Otherwise, on the speed now, if I put a little more inductance, you see that now you get an RLC, and my rise time is not very good. I have lost on the amplitude, and also this thing is oscillating. So very often, as soon as you get some parasitic inductance in this very high frequency operation, this L over R is going to hurt more than the other parameters. And so this is something that is also going to degrade your rise time. Okay. High-speed amplifiers. Interesting to try to now evaluate the response, the jitter performance of the different amplifier that you can use. They have changed name, I'm sorry for that. So this one is the one, again, that you call voltage preamplifier, sometimes called broadband, sometimes called RF, lots of names for the same thing. It's just amplifying the voltage that you see on the sensor. I take this kind of expression, and so the signal that you get at the output is your input voltage, the charge divided by the capacitance, times the gain of the amplifier. If you now use the transimpedance configuration, now you put this value in feedback rather than on the output. It's interesting, but it's an exercise also for tonight to make the calculation, and you will see that classically, we neglect the second term, and this is just the minus RF. When you work at very high frequency, unfortunately, it's the one that gets negligible. And then what you get is very similar to the broadband. So the difference between RF amplifiers and transimpedance for the very high speed response is exactly the same. So for simplicity, this is the one, this is most used in timing application. So this is the one we can do the calculation. You can calculate the jitter. Once again, this is the noise divided by dV over dt. So you bring this to the values that you have. Sorry, it's a bit calculations. Believe me, it will depend once again on the signal duration, the speed of your preamp, and then also the noise, sensor capacitance, and the charge. So you would need to do the calculation to convince yourself. But one thing that you see once you have done the calculation is that there is an optimum, so you can play with the preamp speed in this thing. And you obviously see very quickly that you can, I think it's plotted on the next curve, and you can see that there will be an optimum for the preamp speed equal to the current duration. And so if you match the preamp speed to the current duration, then your jitter is given by this simple formula: preamp noise, sensor capacitance, the amount of charge that you get, and then the current duration only by the square root. On this term, on this equation, there are three terms which come from the sensor, and there is one which comes from the electronics guys. So the sensor guys has 3 times more work than the electronics guys. So they have to minimize their sensor capacitance. That's one way of improving. They have to increase the amount of charge that they give. So this is once again when people are doing LGAT, so they are putting gain in the sensor. This is why, for example, also silicon PM or MCPs have a very good performance. You get a lot of charge. MCPs, you get a small capacitance. Silicon PM, the smaller the silicon PM, the better your jitter will be. And then there is the current duration. And so in silicon detectors, people, they play on the thickness of the detector to minimize the current drift. But of course, when you do that, you are penalized by the increase in capacitance. The electronics guys, the thing they do, they play with the current in their input transistor. So you can show that the electronic noise scales with some theoretical, some physical constants. And the only thing the electronic guys can do is play with the current they put in the transistor. And unfortunately, it only goes with the square root of the current. So you don't gain very quickly with the power. And that's all. Of course, you can do worse. So that's easy to do worse, don't worry. But and so I will finish by just showing 1 or 2 examples. So this is the same curve as before. So this is this expression here, but now which is plotted as a function of the ratio on the rise time to the current duration. Just so that would be the speed of your amplifier. So here, your amplifier would be very fast. Here, it would be too slow. Here, it would be at the optimum. The jitter is the blue curve. The orange one is the noise. So this is something I want to bring your attention to. You see that if you are twice too slow or twice too fast in the preamp, you only change the jitter by 10%. So the bandwidth is not going to do so much after all. But what you will go very quickly is that if you are twice too fast, then you increase the noise as square root of 2. This means that your minimum threshold will be higher. It will be more difficult to see your MIP. So at some point, getting too fast is hurting. So you have clearly to work carefully on the optimization. Okay, you will go to the example and see that what we can do. There are examples of what you get in real experiments. I'm sorry, I did not have the time to go into them, so we will go into the slides. And so just to finish on the second part with the imaging calorimeter, so you can maybe visit, I think there is maybe things on EdgeCal here where you can see imaging things. So in which you have more and more function inside the electronics, including the timing capability. And on the timing performance, there is a lot coming on the sensor side. On the electronics, not so much to do, probably not to be too fast. And so, as you have seen, there is work going to go to, Janet was showing, 10 picosecond accuracy. Sometimes people speak about 1 picosecond. You can say that 10 picoseconds, so sometimes you see nice plots, as was said by Etienne. So you are happy, you have a clean measurement, a preamp with 1 watt and so on. You know where you will have 10,000 channels like that, one oscilloscope to process the data and all of that, and then you get your 10 picosecond. And then now to get the full system to a few tens of picosecond is still something which is ahead of us. And so 1 picosecond is, I hope that you here will see the 1 picoseconds detector in operation. Thank you for your attention.
Thank you. Okay, we are short of the time, so any question, only one question. If anything. If not, then I would again thank to the Christophe with the presentation. So on the beauty of the institute.
Thank you. The introduction. You have to go and visit. Thank you.
And also this one of the Spain.
Oh, yes, thank you.
Yeah, this is the local tribal.
Yeah, beautiful. Thanks again for your invitation. Happy to be here. And I'm, of course, available for question, discussion, and whenever you need.